Hello. Today we're going to take a look at the product and quotient laws for logarithms. Now, for those of you who remember back when you learned the laws for powers or exponentials, it's pretty much the same idea. When you have two exponentials and you're putting them together in a certain way, there's certain rules, and logs, same deal. So let's take a look at what those rules might be. I'm going to start off just by doing a couple examples. And we'll start by graphing some stuff in Desmos and just see how they look. So let's go over there now. And we're going to start by just graphing the four different functions from question one. So the first one is just y equals log of x. Pretty straightforward, looks a little bit like that. Just make that a little bit bolder. There we go. Okay, so the other functions we want to graph, we want to see how they're related, at least pictorially. What do you think the y equals log of 10x is going to look like? Okay, it kind of looks the same actually, it's just a little bit higher. Y equals log of 100x. Any predictions? Again, looks the same but higher. And y equals log of 1000x. Those all look the same to me. In fact, I'm pretty sure I can get all of them to be the same is if I just say that the log of x plus 3 is equal to the log of 10x plus 2 is equal to the log of 100x plus 1. Those all look like they're the exact same function to me. So that's a little interesting observation to make. Or I could go the other way around. If I wanted to compare them all to the base function, log x, I could say that this one is minus 3, this one is minus 2, and this one is minus 1. And sure enough, those work. So the result here that I really want you to get is that all four of those, have the exact same shape. They're just slid up and down a little bit from each other. And is there a relevance to the 10x, the 100x, and the 1000x? I'm guessing there is. Okay, so this doesn't ask us to actually solve anything. It's just they're all the same shape. That's how they compare. They're just, how do we formally say slide up and down? They're all just vertical translations of each other. Okay, so that might come in kind of handy. With that in mind, question 2 is asking us to evaluate a few different logarithm problems. These ones are log base 10, so that should be pretty easy. Log of 100 is just 2. Log of 1000 is just 3. That gives us 5. What is log of 100,000? Well, that would be 10 to the exponent 5 to give me the 100,000, so that would just be 5. Okay, I want you to just look at those two and see if you can see the connection right now. Log of 100,000 is the same thing as log of 100 plus log of 1,000. The two numbers multiply to 100,000, so I add the logs. Okay. How about this one? The log of 9. Now, unfortunately, the log of 9 doesn't work out nicely, but that's why I have a calculator. 0.9542 plus the log of 11, which is 1.041. I want to keep the same number of decimal places, so 1.0414. And if I add those together, 0.9542 plus 1.0414, I get out 1.9956. I'm going to just make a little observation here that 9 times 11 is 99. And the log of 99, if I do it my calculator, is 1.9956. So if two numbers have the same, or two logs have the same base and they're added together, that's just equal to the log of their product. So for 3, suggest a formula for y equals log b of m times n, and I think the answer is just going to be that it's equal to log b of m plus log base b of n. So that means that we can break one log into 2 or put 2 logs into 1, depending on the scenario that we're in. Question 4 and 5 are pretty similar. For question 4, we want to take those logs and subtract them. Well, the log of a million is just 6. The log of 100 is 2. 6 minus 2 is 4. The log of 10,000 is 4. And just a quick little observation, 1 million divided by 100 is 10,000. I got to make that observation the opposite way here. I'm going to do it first. 4,800 divided by 60 is 80. So my calculator says the log of 4,800 is 3.681, and it says the log of 60 is 1.778. 3.681 minus 1.778 is 1.903. Now over here, the log of 80 is 1.903. Cool, seems to work. So from that, can we suggest a formula for the log base b of m over n? And I think the answer is right up here. We just have to subtract the two individual logs. So that's going to be equal to log base b of m minus the log base b of n. Okay, let's use those rules to see if we can simplify some nastier looking things. So log base 5 of 6 plus log base 5 of 8 minus log base 5 of 16. First thing I'm going to notice is that they all have the same base, which is hugely important if this equation is going to work. So now what I'm going to say is that should equal, and I could do this in 2 steps if you'd like, but I think you'll see it doesn't make much difference. Those two I can put together into log base 5 of 6 times 8 is 48. And those two I can put together, since it's same base, by dividing them and saying that's the same thing as log base 5 of 48 over 16. Now I could have done that one step and just said it was 6 times 8 divided by 16. But just to be sure that we're comfortable with it, we'll do it this way. And now that's log base 5 of 3. And if we want to actually evaluate that, which we can, that's just going to equal the log of 3 over the log of 5. And I'm running out of room, unfortunately, so I just got to work over to the side there. Log of 3 divided by log of 5 equals 0.683. At least round it off a little bit. All right, for part B, I don't think we can do too much evaluating since we don't have real values here, but we can simplify that quite a bit. I'm going to just make an observation. We've got adding there and subtracting there, which means these ones here get multiplied That one gets multiplied. That one gets divided. Adding becomes multiplication. Subtracting becomes divided. I think that's going to save us a bit of a step here. So this is just going to be the log of x times y times 3xy over y squared. So on the top, we have 3x squared y squared over y squared, which actually is 3x squared period, because we can cancel out the y squareds. Now, really carefully, or really quickly, just before I do that, I'm going to put a little note here. This says that y cannot actually be 0, because that would give us division by 0. However, if we look back up right here, since log of y would have been undefined, log of 0 would have been undefined, there's no exponent you can put on 10 to get 0. Y can't equal 0 is true. X cannot equal 0. There's other restrictions, but assuming that the initial ones worked, we don't need to put an extra restriction on our final answer. So we can just say that is our full solution. I wouldn't bother stating the restriction of y can't be 0, because the original question has to be valid in order for the answer to be valid, and it wouldn't be if y was 0. Okay, let's see if we can evaluate these without a calculator, and they look kind of nasty, but that means there must be a trick to make our lives easier. So we have log base 8 of 4 plus log base 8 of 16, both the same base, so we're good to go with our new rule. And that becomes log base 8 of 4 times 16, which is 64. And that's a fancy way of saying what exponent do I put on an 8 to get 64, and the answer is 2. Incidentally, the individual two logs there would both give nasty numbers. They don't work out nicely at all. However, the result when we put them together works out really pretty. So our log laws definitely helped us there. For part B, log base 3 of 405 minus log base 3 of 5. Again, same base, so we're good to go. And our rule when we subtract like that says that we divide the two things. And 405 divided by 5 is going to be 81. What exponent do we put on a 3 to get 81? Well, we have 3, 9, 27, 81, so it's 3 to the exponent 4. Again, that one's actually much easier than using our calculator. Much prettier anyway. And the final one, 2 log 5 plus 1/2 log 16. Ugh. That one looks kind of brutal. At least the bases are the same. They're both base 10. So I'm going to remind you that we have that log power law that lets us rewrite things like this. Log 5 squared plus log 16 to the 1/2, which is log 25 plus log 4. Now that we've got the same base, we are adding the two logs, so we actually multiply the two parts together, and we get log of 25 times 4, which is 100. And since we're working in base 10, what power do we put on a 10 to get 100? And the answer is 2. So that one was pretty nasty looking and actually simplified very, very nicely. Will it always be that nice? Not likely, but hey, from time to time, maybe we get lucky. That is all. So we can stop there. You can try some questions. Let me know if you're having a hard time. I will help you as best I can, and otherwise I will see you in the next lesson. Have a great day.